how do we actually find a largest matching? In this video, we run the Hungarian method on a bipartite graph, step by step, and meet König's theorem along the way. Here's the problem. Given a bipartite graph, find a matching with as many edges as possible. Our example has 5 vertices in each part. The top row is x, the bottom row is y, and every edge joins the 2 rows. Recall that a matching is a set of edges, no 2 of which share a vertex. Here is one, drawn in red, 2 edges. The vertices it covers are matched. The dashed ones are unmatched. Could we simply add a 3rd edge? Let us try. One candidate runs into A, which is already matched, and another is blocked at H on the other side. Every remaining edge fails in the same way. Each of them touches a vertex that is already matched. So this matching is maximal. No single edge can be added. But maximal does not mean largest. We saw that in the Berge video. Can this matching still grow? And if it cannot, how would we know? The key tool is Berge's theorem. A matching is maximum exactly when it has no augmenting path. Here's the graph from that video, with its maximal matching in red. The blue trail alternates between matched and unmatched edges, an alternating path. Its 2 endpoints are unmatched, which makes it an augmenting path. Swap matched and unmatched along it, and the matching grows from 4 edges to 5. That is the whole plan. Grow the matching along augmenting paths and stop when none is left. Back to our graph and to its maximal matching of size 2. The procedure we are about to run is called the Hungarian method. It is a single loop. Let us read it next to the graph. It starts from any matching. Ours is already on screen. Then one loop repeats the following 3 steps. First, pick an unmatched vertex of x. The dashed circles mark everything that is currently unmatched. Second, search. From x to y, the search crosses an unmatched edge. From y back to x, it follows the matched one. Edges are scanned from left to right, and a dead end sends the search back. Depth first. Third, if an unmatched vertex of y is reached, an augmenting path has been found. Flip it, exactly as in Berge's video. And when no search succeeds anymore, the algorithm stops. Now let us run it. The unmatched vertices of x are b, d, and e. We begin at b. B has a single edge, so the search crosses it. H is matched. Follow the matched edge up to A. A's leftmost unmatched edge leads to F, and F is unmatched, an augmenting path. Flip matched and unmatched along it. The matching now has 3 edges. The loop repeats. The next unmatched vertex is D. Across D's only edge to J, and along the matched edge to C. C tries its leftmost edge first, through H to B, but B has nothing further to offer, a dead end. So the search backs up. The faded trail stays explored and takes C's next edge. I is unmatched, a second augmenting path. Flip again, 4 edges. The matching has now grown twice. One unmatched vertex of x remains. From E, the search reaches J, follows the matched edge to D, and stops. No augmenting path this time. No unmatched vertex of x is left to try, so the algorithm stops. The result is a matching with 4 edges. E and G simply stay unmatched. How much work was that? Write n for the number of vertices and m for the number of edges. One alternating search scans each edge at most once, and every flip enlarges the matching, so there are at most n flips. Altogether, order n times m. This augmenting path scheme goes back to König, Egervary, and Kuhn, and Hopcroft and Karp later sped it up to root n times m. One question remains. The loop stopped, but could a cleverer run have reached 5 edges? Remember that an augmenting path joins 2 unmatched vertices, and its 2 ends lie on opposite sides, so one end is always an unmatched vertex of x. The only unmatched vertex of x is E, and the search from E has just failed. So the graph contains no augmenting path at all. By Berge's theorem, that settles it. The matching is maximum. 4 edges is the best possible. To finish, one more kind of object, a vertex cover, a set of vertices touching every edge of the graph. Covers and matchings constrain each other. Look at the 4 edges of our matching. A cover must place a vertex on each of them, and they share no vertices. So any cover has at least 4 vertices. This counting works in every graph, not just bipartite ones. Can the 2 sizes always meet? In general, no. In a triangle, any 2 edges share a vertex, so a matching has at most 1 edge. But a single vertex always misses the opposite edge. And so the smallest cover needs 2 vertices. 1 is less than 2. In general graphs, the gap is real. For bipartite graphs, however, König proved that the 2 optima always agree. The largest matching and the smallest vertex cover have exactly the same size. On our graph, the matching has 4 edges, and indeed 4 vertices suffice to cover A, B, C, and J. Every one of the 9 edges touches a gold vertex. Four equals 4, exactly as the theorem promises. And this little cover certifies once more that our matching cannot be beaten. Thanks for watching. If you enjoyed this video, please like and subscribe to support the channel. More graph theory videos are coming soon.